So let's look at this one over here, right here, over here. An open top box is to be made by cutting congruent squares of side length x from the corners of a 20-inch by 25-inch sheet of tin and bending the sides up. How large should the squares be to maximize the volume? What is that volume? That's supposed to be a question mark right there. Oh, that's... All right, so let's see. I think I zoomed in poorly here. What are we doing? An open top box, so at the end it'll look like that, is to be made by cutting congruent squares. So that's this part here to that. For there, that's what it's talking about. And what do we have? Well, what's our first step? Our first step is to write some kind of equation. So, okay. How can I write some type of equation? Well, from the corners of a 20-inch by 25-inch sheet of tin and bending the sides up, how large should the squares be to maximize the volume? In this particular case, we can't really make our, like, I guess, auxiliary equation, just because there really isn't two two pieces of information that we can use separately. It's really just all one piece of information, and it's talking about volume. Like, I'm thinking, what can I do here? So what can I? It doesn't say anything about the the area of the tin. Otherwise, I could do like 25 times 20, and then take out something. But it doesn't talk about that, so I don't need that. It does talk about the volume, though, and the volume of this box, what would that be? That would be side, length times width times height. So really, I need these, and it has little question marks because isn't that nice? But just look, I can get that. I can get that. If this whole thing is 20, and I'm taking out an x and an x, that's 20 minus 2x. So this is 20 minus 2x. And then same thing goes for this. The whole thing is 25. Take away an x, take away an x. So that would be 25 minus 2x. And we're talking about volume here. So the equation that I need to everything is already in terms of one variable. That's how we know we don't have to have an auxiliary equation, because everything is in one variable already. It's just x. So to find the function that we need to maximize, right? Largest volume? Yeah. To find the function that we need to maximize, we just take, let's see, let's zoom out. 20 minus 2x, that's length times the width, 25 minus 2x, times the height, which is just x. And that's going to equal, I'm going to call it v of x. And we want to maximize this. I didn't have to do all the other steps where I'm trying to get it in one variable, or like try and write down some first equation, just because it was already set up for me. So maximize this. So then I'm going to simplify this out a little bit. I'll multiply. So after we've multiplied it out, we can take the derivative. Remember, I'm just finding extrema now. So the derivative, that would be 12x squared minus 180x plus 500. And set that equal to 0 and solve. So 0, and then I guess I can try and factor. I'm going to divide by, can I divide by 12? I can't divide 500 by 12. Can I divide by 4? Yes, I can. So I'll divide by 4, factor out of 4. That would be 3x squared minus, what's 180 divided by 12? No, divided by 4. That's 45x. Plus 125. Whoops, I missed out on some. Oh, no, I took the derivative. Okay. So what am I doing? I'm going to try and factor. Can I factor these? Can I factor? What am I doing? And so then I got that right there, and I'm gonna try this. Looks like I cannot factor. I was just doing it. I just can't factor that. So I go use the quadratic formula. So I get x equals the opposite. That's 45 plus or minus the square root of 45 squared. All of that divided by 6 there. And what? Well, I mean, technically that's simplified, but I'm going to simplify it a little bit more. So that would be, what, 15 over 2. I'm going to split it up. Plus or minus the square root of 525 over 6. This is crazy. This is crazy. But what am I getting here? How large should the squares be to maximize the volume? So I'm thinking did it, but I'm gonna check and see, make sure that the squares. Oh, so definitely the volume is maximum when x equals this, but I'm gonna check with my sign chart. So if I do a sign chart here, I would say the critical point. I'm gonna get approximations for these. So those are my approximations, approximate values. So what am I going to do now? I'm going to make a sign chart just to check and make sure that this is a maximum. And then I'll check to see if I have any bounds, any endpoints. What the heck does that mean? Oh, well, let's see first here. 3.681 and 11.319. Those are my critical values because that's where the function's derivative equals 0. So my test points, I'll say 1 and 4 and 12. And then let's see if my derivative sine of v prime. So I'll plug it into this. What do I get? I plug in 1, what do I get? I get a positive, definitely. Plug in a 4, what do I get? So I get a negative when I plug in 4, and let's see, when I plug in 12. I get a positive. So what happens? What did I want? I wanted my volume to be maximized. So I'm looking for a local maximum. So this is going up and then going down. This one is a minimum, so I know I don't need to include that. So great. I have a local maximum at 3.681. With a value of whatever I get when I plug it into the actual volume formula. But let's think about this. I do need to consider bounds because this is a physical object. We can't have x being like 0, otherwise we wouldn't make a box. So x cannot be 0. So I'll have smooth parentheses there. And I also, well, what's the most restrictive? I can't have x being, like I'm looking at these sides right now. If x was 10, this would be 0, right? So like that comes before this. If x was 10 here, that'd be fine. But if x was 10, I would have problems because I wouldn't have a box anymore. So those are my bounds. But again, I can't include 0 because I wouldn't have a box, and I can't include 10 because I would have a side length again of 0. Wait a minute, could I plug in 0? If I had 0? Oh no, I wouldn't. I can't have 0 because if I didn't cut anything out, I have nothing to fold up. So that doesn't make sense to have 0. So yeah, I can't have 0. I can't have 10. Hopefully that makes sense. And we have max at approximately, that's not how you do it, but at x approximately 3.681. And if I plug this in to my volume formula, volume of, what would it be? So there it's that 820.528. What are my units? Inches cubed. So that would be inches cubed. Holy smokes, that was a lot. So that would be inches. So what the heck is this saying? First of all, let's think. It was asking for a maximum volume. So what did we do? We got a volume equation, and it was already in terms of one single variable. So that was nice. And then we take the derivative of that so we can find the maximums or minimums. And in this case, we wanted to find the maximums because it was asking for a maximized volume. So we take the derivative, set it equal to 0 to find critical points. I needed to use the quadratic formula for that, and we discounted one of the things just because it was a minimum there. And also, it wouldn't make sense to have x being that because we did consider some bounds. X can't be 0 because then you wouldn't be cutting out any corners and you wouldn't be able to fold anything up in your box. X wouldn't be 10 because then the side length would be 0, and that doesn't make sense either. So we found that the only spot where we had a maximum was at when X approximately was 3.681, and if I plug it into the volume formula, I get 820.528 inches cubed. And that's the end of that. I'm done.